Okay, so I'm going to make a start. Today we're talking about template metaprogramming. And this follows on from what we've been talking about for the last couple of weeks in terms of templating and in terms of partial template specialization and some of the stuff we've talked about in terms of the compiler and how the compiler operates. And what we've looked at least over the last few weeks, is the idea of when you have templates defined, at compile time, the compiler goes and uses those templates to go and generate up additional functions. So basically, the template is a recipe or prescription for how to compile some code under a certain set of circumstances. And so you can almost consider templates as being instructions to the compiler about how to write its own C++ code. And that's very much what the idea of metaprogramming is. Metaprogramming is the writing of computer programs with the ability to treat other program code as their input data. It means that a program can be designed to read, generate, analyze, and transform other programs, or, and it's more what we're going to be looking at, being able to do part of the work that would normally be done at runtime at compile time. Now, a meta language is the language in which a meta program is written, and reflection is the ability of a programming language to be its own meta language. And because we're focusing on C++, we're going to focus on C++ metaprogramming. So C++ templates can be used to metaprogram other C++ code. So basically, the templates end up coding other templates and other C++ code. And then we've got for object language, which is the language of programs being manipulated. And so if you're building compilers in particular, compilers work heavily on metaprogramming. They take your high-level C++ code and transform it into some sort of lower-level machine code, and that machine code gets transformed again into ones and zeros that operate on the CPU. So compilers are very good at this metaprogramming type ability. In fact, if you go and study how compilers work, you'll learn that the way in which compilers are tested by being able to have a compiler compile itself. So the way in which compilers get built is somebody goes off and programs, say, a new compiler. They compile that in, say, GCC to start with. And then once they've compiled that version of the compiler, they recompile the compiler a second time in the compiler that they've just built. So it becomes quite a recursive process. This Python, Ruby, Perl, they're also metaprogramming languages. They can modify their own instructions at runtime. And so with C++ metaprogramming, we look at a lot of templates, and we look at a lot of static values, so compile time calculated values and how we do it. And so when you first of all ever go and do a Google search for how to do C++ metaprogramming, 99% of the time you'll see this example, how to compute factorials using a metaprogram. And so factorials, I'm assuming everyone knows what factorials are, but if you don't, factorials are just a number multiplied by all the preceding numbers. And what that means is the factorial of 3 is 3 times 2 times 1. Factorial of 4 is 4 times 3 times 2 times 1. Okay, it's got nothing to do with metaprogramming, it's just this nice pattern. And we can actually think of factorials in terms of calculating them as being, say, 6 factorial is 6 times 5 factorial. And 5 factorial is 5 times 4 factorial, and so on and so forth. And so that's kind of quite recursive. And now I could easily create a recursive function to do this, but that means at runtime, what's going on at runtime is every time I want to calculate the factorial or something, I'm having to go through this recursive process. And recursion, it's fun. It's a little bit confusing at times, but it is fun. But say if we have a program here, and at runtime, or at compile time, sorry, at compile time we know we need to calculate out 6 factorial. Is there a way we can calculate this at compile time instead of runtime? And we can, using this template metaprogramming. And so we create a struct or a class. The reason why I'm going to use struct everywhere is just because I don't have to worry about making these things public and private. Everything in struct by default is public. But struct and class are basically the same thing. So I'm going to create a struct, and the struct's going to contain a static constant long with the keyword or the type name value. This value is going to be assigned n, which is, if we're starting first time through, 6. Okay, 6 times whatever factorial n minus 1 value is. And so this is going to recursively keep generating different instantiations of this template at compile time. And we have the partial template specialization for the case where it gets passed in 0. And so 0 factorial is 1. And what happens is, the way in which this recursively happens, so it goes down, it finally gets to this factorial of 0, gets a 1, recursively works itself back out. Okay? You don't have to write this as a metaprogram. You can write this as a recursive function, and the behavior would be the same. You need that recursive breakpoint. And the recursive breakpoint we have in computing factorials is when we ask for factorial 0. Everyone following so far? Okay. And so what happens is at compile time, this factorial 6 gets calculated out. And because these are static consts, at runtime, basically that just gets substituted in for whatever result of 6 factorial is. And so, say I had 2 lines. Okay, I'm going to bring this code up. Okay, I'm going to bring this code up. Factorials.cpp. Again, you can download this from the course website. If I show it up on the screen. Okay, if I do 2 lines like that. Okay, factorial 6. What's going to happen straight away is, again, at runtime, because this just gets substituted in during the compilation stage, I don't have to go and calculate for factorial twice. Okay, it already knows it's there, it gets calculated again. If I calculate factorial 6 and then want factorial 5, again, that's no extra compilation because the previous factorial 6 calculation is generated from meta templates already for us to work with. And so it just gets the result like that. If I want to calculate for factorial 7, it has to generate at compile time 1 additional template, but then it can use ones that's calculated in the previous steps. And so this is very, very, very fast. Okay? The compilation stage slows down because there's quite a bit of overhead in having to calculate out all those meta templates. Okay? As you can probably see, it took a couple of seconds to run, so that wasn't the world's fastest compilation. But when I run this code, okay, it's already pre-calculated, so it comes out very fast. It's not having to do any of that recursion at runtime. Now, a few weeks ago, we saw the idea of const expressions and how they were introduced into C++11. C++11 allows us with const expressions to do exactly the same thing at compile time, but without meta templates. So what you're going to be seeing today is a lot of meta templating stuff, and then a lot of C++11 or even C++14 ways of doing the same stuff at compile time without the confusion of having to write meta templates because they're hard to understand. And so this example here is your standard way of calculating a factorial if you didn't have meta templates. And so if I lose the word const expression off the front of this, okay, if I lose the word const expression off the front of this, and I go and compile it, okay, it compiles fine. At runtime, oops, that's fine. At runtime, it goes and calculates. Okay. Now, if I make this factorial a little bit bigger, instead of doing 6 factorial, I'm going to have to make this quite big. Let's say go do 100 factorial. Okay. Oop. Something went wrong. I'm not sure why 100 factorial is 0. That's kind of weird. Let's just try 101. Still 0. It's nothing like your code not working on a live demo. 0. Okay, there's something wrong. Am I exceeding max int? Oh, I'm exceeding max int. Okay, so that's 0 because factorials blow up pretty quickly. So I pretty quickly exceeded max int. There you go. So if I change this from, say, an int to a long, okay, change that to an int to a long, this should still work. It does. And now if I say make factorial 20, okay, well, that's a big number. Okay, factorials get very big very quickly. But you can see at runtime that's having to calculate. Okay, now my computer's quite fast, so it's still calculating that quite quickly. But say I whack this into a for loop, so for int I equals 0, I less than, I don't know, 100, plus I. Okay, make that and run it. No. This damn computer's too fast. We'll get there. Okay, so he took a bit of time to run, okay? And I can keep making this bigger, and so it's going to take, okay, here you go. So now it's taking certainly a while to run, okay? Because what's happening is every time through that for loop, it's having to at runtime go and calculate out that factorial. That seems pretty dumb because basically we're doing the same calculation again and again. If I do this as a const expr, this will happen at compile time. And so it compiles like that, run it. Okay, this has got to take some time to print out. But basically what's happened is the performance time of this is different. Okay? So maybe take out for printout, okay? Yeah, I can add a delay in a function. I can also take out a printout and hope it for optimizer doesn't get to me. Okay, now it's possible that optimizer will optimize this out. Okay, see how quickly that one ran? Let's just see how quickly this one runs. And the optimizer is getting to me. Okay, so what I'm going to point out very quickly is the optimizer, and we're going to talk about optimization, is very, very good at optimizing things out. Okay, even when I don't necessarily do anything, the optimizer is very, very good at optimizing things out. Let clean. Okay, it still runs too fast. Okay, so let's go to trust methods, okay, in terms of the optimizer's behavior. Okay? But what we've got is, we've got a metaprogram here, which calculates stuff at compile time. With a C++11 style way of calculating stuff, it still happens at compile time if const expr is there or not there. If const expr is not there, stuff happens at runtime. And if we change those values, then we need to, but if those values are constant, then they should stay constant. Okay, so we've got that idea so far, right? So still talking about the compiler and the optimizer, imagine I have this problem. Okay, I've got a large Euclidean vector, okay? And for calculating the dot product for the Euclidean vector requires me to calculate the first position in the two vectors multiplied plus the second position in the two vectors plus the third position in the two vectors, and so on and so forth. And I might have some sort of loop to do this. So here we go. We've got this calc dot product loop. Okay, takes in Euclidean vector A, Euclidean vector B, and the number of dimensions. Okay, and then I go into a loop that says, okay, here's the result for int I less than 0, I less than number of dimensions, plus I. Go through that loop. Okay. Now what we've had to do is we've had to create this temporary variable I. Stick this temporary variable I into memory, and every time through this loop we've got to increment I. Now, again, modern computers, they're pretty fast, so this code's going to run pretty quickly, okay? But the question is, can we go faster? And so what the optimizer does is the optimizer is able to take a look at this loop and is able to do a process called loop unrolling, which is to go, if I know the number of dimensions at compile time, okay, I can eliminate this variable I by just basically modifying this code to just go, okay, yep, double result is equal to this position, plus equals this one, plus equals this one, and so on and so forth. And the second version, the sketch of how the second version works, is going to run much faster than this top one. Okay? And so Optimizer is smart. Optimizer analyzes your code and works out how can I eliminate variables, how can I speed it up, okay? As you've seen here. There's different settings to how you can set Optimizer to work, okay? So by default we use a thing called O2. There's different settings on how that works. You can take a look at that. That's not the point. The point is to understand the idea of how this loop unwinding works. So we understand this, because this next slide's going to be fun if you don't. Okay, so we've got the idea of loop unwinding. The Optimizer's going in and basically eliminating this I variable. Yep. Let's go do the same thing with Metaprogram. So this Metaprogram, okay, now to be clear, you actually wouldn't write this Metaprogram probably by yourself, okay, because again, the Optimizer's doing some cool stuff, but if we were to try to do loop unrolling ourselves, the Metaprogram again looks a bit like a template. What is a template? And imagine that we have a main function that generates us two vectors, okay? These vectors are just three-dimensional interarrays, and we want to calculate the dot product on these things, okay? Because we know all this data at compile time, it'll be faster for us to have this dot product calculation at compile time than it would be to have to go and calculate this at runtime. And so, very similar to our factorial, we're going to do some recursive templates. What we have is last time we saw that we had a type. Okay, so we just had a type. Last time it was a value, it was an int or a log. This time we've actually got a function. Okay, this time we have a function. But a similar idea, we've got a templated class, dot product, that's got this function in it. Okay, this function's actually returning a type t. Okay, so we can modify this to, instead of just being ints, it could be longs, it could be doubles, it could be something else. Okay, but we've got the dot product coming in. Again, this is recursive. So what's going on is we calculate A star times star B. Okay, so again with arrays, if you just dereference the first part of the array pointer, it just gets you the first icon in it. And so we can just recursively keep calling this with just +1. Okay, so it's just using a little bit of pointer arithmetic. Until we get down to a point where the number of dimensions we're asked to calculate drops to 1. So what that's saying is we start at one end, so we start at, so we've got 3 dimensions, we start at 3, we calculate position 1 of that 3-dimensional vector, we then pass down, saying we've got a 2-dimensional vector, but we pass down the pointer 1 position further on, so we do have a 2-dimensional vector, calculate that bit, and so on and so forth. It's recursive. Now again, you might need to go and study some of this later on in terms of how it works. I don't expect you to have to program this, okay? But understanding the process of how these templates are working, how they're recursive. And so what we have is we have a function. There's also a template called dot product, and we can go and calculate the dot product on these vectors. And what's happening is, again, this is compiling at compile time out for values. And so at compile time, this dot product free int result gets the result of A star times A star, wait a second, A star times A, so A star times B star plus the result of this dot product here. This dot product down here gets taken out, okay? This dot product here gets taken out and substituted in like that, and so on and so forth, to the point at which it can statically calculate the entire result at compile time. So our compilation is a little bit slower, but at runtime, our program just runs really quick because it doesn't have to go and manually calculate this out. Yes?
So just to clarify, this does nothing if you're getting at runtime input?
Yeah, if you're getting input at runtime, this doesn't do anything, but I've got an example coming up that does some cool stuff with that.
So
Okay?
some sort of optimization for creating these templates that
Sorry, can you say it again?
So using this template, is there any sort of optimization for runtime inputs?
Yep, we're going to get there. Okay, so we're working towards runtime inputs. Okay, but we need to get to ideas first. And unfortunately, like last week, I've got lines going through the screen, and I don't know why. I'll switch to both projectors. But, okay, that's kind of annoying. So there's going to be lines going through that screen. I'll switch back to the code when need be. Okay. So we're understanding this process so far again. Okay. So these templates are recursive. They're being compiled out at compile time in order to calculate static values to speed up our runtime stuff. Okay. So we've got another example here, and this next example is calculating the square root. Okay. And to calculate the square root, what we're doing is a process that, I do need one of these things up on these screens. Let me see what I can do. See if I can bring it up on that one. Okay, so I've got my, okay, I'll split the frame. Okay, so this calculating the square root, let me back up. Calculating square root is difficult, okay? The way in which calculators work to calculate square roots is historically they might have had big lookup tables to just know the values already, or again, the process is a number of different ways of doing it. Here's one way of doing it, which is to calculate the square root. You basically get the value, you divide it by 2. You then, that value divided by 2, you multiply it by itself and see if the result is greater or less than the existing value. And then what you do is you divide it by 2, and so on and so forth. And so this is an expression here, which basically is in a red. N is equal to the midpoint times the midpoint. Okay? So n less than midpoint. If it's greater, if it's greater than midpoint, then you call this recursive version. If it's less than, you call this recursive version. Okay? Now this is a little bit hard to read because of the crazy question mark and the colons and things like that. Okay, but that's just a one-line if statement. Okay? And that one-line if statement, or that one-time expression, is working out which one of these next templates to call. So what we can do, let me just fix the code because I don't want the square root of 5,000, that's going to be a nightmare. Let's go calculate out the square root of 16. Okay. And so what that's just done is that compile time, it's calculated out the square root of 16 and telling me it's 4. Again, at compile time, so this is very, very, very fast. Again, I can whack that into a big long loop, have a version of this that runs at compile time, and that's going to be slow because this is a compile time optimization. It's going to be very, very fast when it goes and runs. So this is the idea of these metaprograms. Again, now we've got expressions that they can calculate. Okay, so everything here is just happening at compile time. It's all static value happening at compile time, but it allows us to speed up our runtime code. And so what you're seeing that's going on is inside the call to see out calculate square root 16, it's expanding. And what it's doing is it's calculating a couple of things. The code before had 2 values. It had a mid value and it had this result value up on the expression. At compile time, first time round, it calculates the mid value, which is 1 plus 16 plus 1 over 2 is equal to 9. And calculating the result of 16 being less than 9 times 9. Now 9 times 9 is 81. Is 16 less than 81? It is. So call square root 16, 1, 8. Okay, and again, the expression up here said we've got these low and these mid values. Okay, so the 8 comes from 9 minus 8. So 9 minus 1 is 8. Go like that. Now call the result of square root 16, 1, 8. Okay. Next template gets initialized for midpoint. 1 plus 8 plus 1 over 2 is 5. Is 16 less than 5 times 5? Well, 5 times 5 is 25. 16 less than that? Yes, it is. So call 16.1.4, and so 16.1.4 gets called, and so on and so forth. And so finally you get down to the specialization, which is 16.4.4, and that's what terminates. And the reason why it terminates at that point is because we have this partial specialization, which is different to this top one. So this top one we had N and low and high. The bottom one we had N and M and M. And so this partial specialization happens when this low value and this high value gets equaled. Again, you don't have to understand exactly the math behind how this works. What you're understanding is how the templates are being calculated out at compile time. And so this metaprogram for how these things work at compile time, again, is just going through and calculating this expression. Okay? Everyone following so far? So basically what we're showing you is templates are very, very, very powerful. Okay? Now, like I showed you earlier, we can do a C++11 const expression version of this. And so by going static const xpr all the way through this code, it's the same thing. Okay? Only this is using const expression rather than using the templates. Now, there's a couple of benefits of using a C++11 version. Okay? You don't need the class variables storing the midpoint, which was part of a really confusing thing earlier. Okay? And so it's a little bit cleaner, a little bit easier to read. However, you still have this horribly long expression through the middle of here doing that bulk of that square root calculation. And the reason why it has to be that one-line expression is because C++11 const expressions and the meta template up here, they can't have if statements in them. Okay, it can't be an if statement. An if statement can't be compiled statically at compile time. Okay, so they're a long version like that. But the really cool thing, the really cutting edge thing, is in C++14, which is the most recent standard, you can have a C++14 version with if statements in them. And because this is a static const expression, this whole if statement gets calculated out, this whole auto value gets calculated out, and again, you can calculate the square root at compile time like that, provided this square root 16 is defined as a static at compile time. Okay. Now, you can download this code, you can attempt to run this code. My advice to you is good luck. The reason why I say good luck is even though GCC 4.9.2, which is the standard that we're defaulting on, the standard that's installed on the school computers, is meant to support C++14, unfortunately this doesn't compile. So I managed to get to compile on a thing called CLang, which is just a different compiler, and that compiles. But let me show you. So square root 14 is my version. Let me just quickly change my make file.
You don't have your code up.
Yep, I don't have my code up. Thank you. Let me switch across. Let me see if this is going to stay working. Okay, so I've got my make file here. In square root 14, I'm going to first of all give you G++. Okay, and I'm going to go say make square root 14, and it goes. What does it say? It goes body of const expression is not a return statement. Okay, and the reason why body of the const expression is not a return statement is because it's got all these if statements all the way through it. Whereabouts for C++11 version, see how it just had return at the start? It was one-liner. Okay, so the C++11 version, which according to my make file here, square root const expression, standard equals C++11. Okay, this one will compile fine. Let me show you. Okay, that one compiles fine. That's for C++11 version. But the C++14 version, even though C++14 is meant to support this, the GCC doesn't. If I change this to, say, C++11, still doesn't compile. If I change this to C++1y, which is C++17, still doesn't compile. If I change this to a different compiler, okay, so meta templates and const expressions and up-to-date things like this are very much compiler dependent, so I change my compiler, I make it and it goes away and compiles and calculates out that square root. And it does it like that. And now I run this and it calculates and runs. Okay? So some of the stuff in this set of lecture slides may not run on your computer. Okay? Because these things are tricky for the compilers to even be able to process and be able to understand. Okay? But what we're focusing on again is the ideas behind this, okay? So don't necessarily think that this code's got it. Well, the code should run if you have an up-to-date compiler, but I'm not expecting you to go write this sort of code. It's understanding this difference between the compile time optimizations and the runtime optimizations. Okay, who's still with me? Everyone still with me? Yep, cool. Okay, this is about to get more fun. We looked at template meta functions. Oh, sorry, not meta functions, but we looked at template types briefly on Monday afternoon. Who can quickly remind me what a template is? Should be pretty straightforward. What's a template? I'll give you a hint. The line in red will help you out. What's a template?
Is it just a template where one of the parameters is a template itself?
Yeah, so it's exactly that. It's a template where one of the parameters coming in is a template itself. And so what we saw on Mondays, we had for stack class, that took in the default argument for what sort of container it should hold, and the container itself was a template type. And on Monday, that wasn't particularly helpful because what we wanted is we wanted a way of being able to make sure that worked with a vector or whatever and ensuring that type T still worked. Okay? But today, this template syntax is going to help us with this particular program we're going to look at. So this program, again, start at the bottom and look at main. Okay? And so what main is doing is it's calling this class called accumulate. And it's passing in two things. It's passing in an int, and it's passing in another class. And so accumulate for identity passes in 4, and it passes in this class identity. And this class identity just says val equals n. Okay? So this just passes this value n through. We go take a look at the template parameter up the top. That had an n there and takes an int. Okay? And this class f just means that what is being passed in is a templated class. Okay? So you've seen type name all the way through things. Earlier I said that you can substitute type name with class. In this situation, this actually has to be the word class there. You're passing in a templated class. And so accumulate for identity, the way in which this works, is it just goes in sums, 4 plus 3 plus 2 plus 1. And so accumulate, when we accumulate something, it's just to add up or sum up the values. Accumulate for square, you go look at the square function. For the reason why it's in speech marks is these aren't functions, they're templates, okay, but they get passed almost as functions into meta templates. And so square is n times n. And so that's 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, and cube is the same. It's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And so what we've got with this meta template that's taking in another templated class is basically it's behaving as some functions going in. Okay, so this is kind of getting quite tricky at this point in terms of the code. But again, what it's helping us to do is it means that at compile time, again, if we know what we need to sum up somehow, we're letting the compiler do all this optimization for us. And again, I won't compile it, don't need to, but you can trust me that this compiles and this runs. Okay. And so what you're seeing is, again, how this is working. Let me just jump back to this slide. Okay, is the value of accumulate is just recursively calling accumulate with n minus 1. So you see how these things are very recursive. Every example we've seen so far has some degree of recursion in them. Okay? And they're stopping when they hit a particular endpoint. And this particular stopping criteria, this particular endpoint, is when the int is 0 and then just pass it straight through. Okay, so these things are very, very recursive. And so, say we asked it to pass in the calculation of identity 4, goes identity, identity 3, identity 2, identity 1, identity 0, add those things up, you get to 10. Okay, so that's basically how those functions are working. Okay, so see how the accumulate and the f of n is being passed in. Okay, whereabouts f over here was the class template being passed in. So this is how this whole n value there gets passed across into the f value there. Okay, so this is again quite tricky in how it works. Okay, but it's doing some really cool stuff at compile time. It's able to calculate these values out at compile time. And there's a link there to go take a look at how template arguments can work more with meta templates. Now I'm going to show you something cool. I'm going to bring it all together in the next 5 slides, okay? But the reason why I'm showing you all this is this is the power of C++, or the power of templates and partial specialization and all this sort of stuff. And it's used extensively in sort of high performance, high powered computing, where, say, in graphics libraries or in basically real-time systems, stuff that needs to run very, very fast, if you are able to calculate something once and use that same result many times over, your code's going to be much, much, much faster than having to do all the stuff at runtime. So we saw that a little bit earlier on with factorials, okay? Even though my computer's too fast and didn't really show you, but you got the idea, okay? So these things are really important to writing high-speed code, okay? Again, I don't expect you to write meta templates. I expect you to be able to just understand from rough, very high-level idea of how they work, okay? And in terms of exam questions and stuff like that, there's not going to be a huge amount of metaprogramming in the exam. What there is going to be is more questions to do with partial templates and stuff like that, like we've seen over the last couple of days. So in terms of today's stuff, I don't quite expect you to understand it, or I expect you to see just how powerful this stuff can be. And so now what I'm going to do is I'm going to bring it all together, and we're going to look at bubble sort. Now, can someone give me the idea of how bubble sort works?
Compare adjacent elements and switch them out of order.
Yep, that's basically it. So work through some sort of set and start at the start and go through it. If the thing's out of order, you swap. You keep going down. And what happens once you've gone over the thing once? What's the next step?
Go over again.
You go over again. And when do you stop?
N times.
You do it n times. Okay, so a bubble sort basically it starts at the start of a container, it steps its way down a container, swapping things that are out of place. Okay? And it repeats that process n times. Is it fast?
Depends on N.
Depends on n. Yep. But it's a way of sorting stuff. Now we're going to do a bubble sort in meta templates that, excitingly enough, particularly for Brady, we're able to change the value at runtime. Okay, so we're going to bring this all together. So what I have here is I have a function, first of all, just to swap 2 values. Okay? And this function to swap two values is a static inline void. Okay, so it's not a constant anymore. It's a static inline void function that's calling standard swap. Okay, so this isn't a meta templated function. This is just a standard template function, but it's going to be calculated at compile time, different versions of it. Okay, but this first function that you're seeing is not a meta template function in the fact that it's static, because it's not. Sorry, it's static, but it's not const, okay? The next thing that we're going to see, though, is this bubble sort loop function, which has a static const bool as a result of this expression here. Again, you don't have to care about what j and j less than or equal to I minus 2 is. It's just basically a bool. Okay, this bool is going to be dependent on the values of I and j coming in. Okay, so this bool part is part of the meta template. Again, this loop in here isn't part of the meta template, but is dependent upon the results of some of these meta templates going on. Okay, so this int bubble sort loop is dependent on the result of go up here in this expression that gets calculated out. Okay. Now I didn't actually write this code. Okay, I actually don't know who wrote this code. I think it's just a really fascinating example. Okay. But there's quite a complex expression going on there, working out what template to calculate. Okay, and so this non-meta template function that will run at compile time, will run at runtime, is dependent on some compile time optimizations and some compile time meta templates. We then have a partial optimization for the case in which the loop finishes. Okay, and there's a slight error on that slide, but let's bring up the source code and show you. Okay, so this error on the slide, just at the end of here, is just missing the open and close bracing. My code up there, that's just what it's missing. So in the case that the bubble sort is swapping nothing, just do nothing. Okay, so again, it's that end criteria. We're going to work our way down the bubble sort loop, work our way down the range. When we get to the end, we just need to know to stop. Okay, so that is our stopping criteria. Then we have this recursive function here. I've said recursive meta function. It's actually not a recursive meta function. It's just a recursive function. But it depends on the meta functions to keep looping until we're sorted, or to go down to n times. Okay. So what it's doing is it's calling the loop, and then the next time around it's n minus 1, calling int bubble sort. So it's calling itself. So it's recursive. Okay. And finally, we just have a end function again for when to stop that loop. Okay, so we've got a whole lot of meta functions going out that are combining meta functions with runtime functions. Okay. What we're now going to take a look at is how to actually run this at runtime. What we're going to do is we're going to create an array of 4 elements. Statically create an array of 4 elements. I'm then going to call int bubble sort for sort A. What this does is for int bubble sort 4, until that point, that is the meta template part of this code. That is going to cause the compiler to go and calculate out the ability for this program to be able to do a bubble sort on arrays of 4 elements. The sort function is the bit it gets called at runtime. And so at runtime, 3125 gets called, and we can go and print out those values after they've been sorted. Now, because that sort gets called at runtime, I can go and change the value of A0. Say I give it 100. Okay, so what happens the first time through, this 3125 gets sorted and prints out 1235. Now I'm going to replace value 1, which is in position 0, with the value 100 at runtime. I'm going to do that. I'm going to call sort again, and it's perfectly happy. And it goes and sorts it at runtime based on the meta template that happened at compile time. Again, you don't necessarily have to follow the code, but you're following the ideas of what's going on. Okay? So let me show you. Let me just make bubble sort. Okay? Now I run bubble sort. There you go. Runs like that. What I could also do if I really want to, and I'm probably going to stuff this up, but if I give it what's the arguments that need to go into main? int argv, is it? Argc and char star, star, yep. Argv, yep. Okay, so if I pass in some arguments, say if I change this to B, at runtime I need to convert the char star down to a, okay, so I'm going to call standard 8i. Okay, I'm hoping this is going to work. I'm going to call that on argv1. Okay, I'm just going to compile this, make sure it compiles. Okay, it does. Now I'm going to call bubble sort. I'm just going to give it value 234. Bang. At runtime, see how that works? Okay, so just to prove that that isn't a compile time optimization that's going on, I can change the values. Okay, I could even do this. Let's do it out 4 times. Okay, so I'm going to now take in 4 values. Someone want to give me 4 values? -7. Okay, let's see if -7 works. Bang. It works. Now, why would you do this and not just do a normal bubble sort? Why would you go through all the pain of all this metaprogramming not to just do just a normal bubble sort? Does anyone want to think about what the speed of that runtime sort it actually is? Oh, I actually don't know, but you want to just think about, okay, actually no, what's the complexity of bubble sort normally? Is it n squared? Okay. What do you think the speed of that is?
Also n squared.
It's not quite n squared. I think off the top of my head it might be n log n. Someone else can work it out for me. This is what actually happens at compile time. Here is my bubble sort at compile time. This definitely is an n squared. What it results, all this thing gets optimized down and it ends up looking like a function like this. Bubble sort 4 is it n log n, is it? I don't know. And what it does is that the first 3 lines is your first loop through. The next 2 lines is the next loop through, and the last line is the final part. And so this whole meta-templated version of bubble sort is many, many, many times faster than the normal bubble sort, if you were to do this all at runtime. And so this meta template, it's gone done all this stuff for us, and so what we've needed to know for this meta template is we needed to know the size. So we needed to know that this is going to be a 4-dimensional array. We needed to know the size at compile time, but we haven't needed to know the values. And so we combined this meta template with the static information with runtime information for how it actually goes and works. Who thinks it's cool? Yep.
What if you didn't know how long?
What happens if you didn't know how long? You would probably have to compile out some huge version of it. So what I had to play with earlier today was to say, okay, well, say I now only have a 3-dimensional array coming in, and I've compiled it a 4-dimensional, what happens? And so say I lose at 65, okay, I run this, and it's segmentation. That didn't happen earlier. Oh, there you go. I have to change that to be version 3 there. Yep. Make. Okay. And see how this bottom version has gone and only done it on 3. Okay? So values less than what I was compiling out work fine. Values higher don't. And so what we did is we this morning took this out to say generate this bubble sort of up to, I think we did 100. I'm hoping I'm not going to crash my computer right now. So 100, look how long this is taking to compile. Okay? So this is the trade-off of the runtime versus compile time. Did you guys see how long that took to compile? Okay? And that was only with 100. It gets much slower the more you go. Yep.
You don't actually have to run it on this. Like, you don't have to sort actual things, right? For the generating the template.
No, I don't have to sort actual things for generating the templates. But what's happening is generating all the different meta functions for generating the